Hello everyone, welcome back to the fast track revision series of UGC NET Electronic Science. In this video we are going to learn about asynchronous counters. Okay, so asynchronous counters, they are also called as ripple counters. Asynchronous counters are also called ripple counters. Okay, if you are first time to my channel, please consider subscribing and don't forget to hit the bell icon to get video notifications from my channel. Right, we'll see the operation of asynchronous or ripple counters. The first point which you have to remember is how asynchronous counters are formed. Okay, so group of complementing flip-flops, group of complementing flip-flops with output of first flip-flop which is usually LSB. Okay, so output of first flip-flop is connected to clock input of next higher order flip-flop, clock input of next higher order flip-flop. Okay, and so on, it continues. It is the output of the next higher order flip-flop is connected to the clock input of next higher order flip-flop. If it has 3 stages, the output of second stage is connected to the clock input of the third stage, and so on. This happens. Okay, so this type of counter is called as asynchronous counter, asynchronous counter or ripple counter, asynchronous counter or ripple counter. Right, so very important terminology. Group of complementing flip-flops with output of the first flip-flop connected to the clock input of next higher order flip-flop. Okay, higher order flip-flop. Okay, and so on is called as asynchronous counter. Okay, so how are you going to have this complementing flip-flops? So complementing flip-flops can be obtained by J is equal to K is equal to 1. Okay, so when J is equal to K is equal to 1, what will happen? Qn plus 1 is equal to Qn bar. So this we have learned from JK flip-flop. So output will be complemented. Suppose if your Qn is equal to 0 and if you are applying J is equal to K is equal to 1, then Qn plus 1 becomes 1. And again if you continue it will again becomes 0. So it will be complemented continuously. So group of complementing flip-flops can be obtained. The first chance is J is equal to K is equal to 1. Second, T flip-flop. If you use T flip-flop and make a T input as 1, then also Qn plus 1 is equal to Qn bar. Okay, so the third possibility is by making D flip-flop. So you can use D flip-flop also in order to get the complementing flip-flop. But what you have to do is you have to connect Qn bar to D. You have to connect Qn bar to D. Okay, because D is equal to Qn plus 1, D is equal to Qn plus 1, and now D is connected with Qn bar, so it is also equal to Qn bar. So now again Qn plus 1 is equal to Qn bar, which is the same condition which is obtained from first 2 cases also. Okay, so with these 3 cases, in these 3 cases we will get complementing flip-flops. Okay, so this is about asynchronous counter. So asynchronous counter is generally made up of complementing flip-flops with output of first flip-flop connected to the clock input of next higher order flip-flop. Okay, so we'll see that. Now this shows you the 2-bit asynchronous counter. Okay, so 2-bit asynchronous counter. 2-bit means you are using 2 flip-flops here. So I'm using here JK flip-flop. The first one I have taken. Okay, so complementing flip-flops is obtained by J is equal to K is equal to 1. So I have connected it with a wire here. So same wire is given for this and also for the first flip-flop. So I'm connecting it with 1 high, that means some VCC value, some 5 volts, practically we'll call it as high. So practically we'll connect it to some VCC, so that always the flip-flops will be in complementing mode only. Okay, so this is how we can obtain complementing flip-flops, the word complementing flip-flops. And second condition, output of the first flip-flop is connected to the output of next higher order flip-flop. So this is your LSB bit, right? So this is your LSB bit. So output of this is connected to clock input of the next higher order flip-flop. Since there are only 2 here, so the output of first flip-flop is connected to the clock input of the next, that is second flip-flop. Okay, so this arrangement is called as asynchronous connection. Asynchronous connection. Why it is called asynchronous connection means 2 flip-flops are there in 2-bit synchronous counter. 2 flip-flops are there, this flip-flop and the second flip-flop. So these 2 flip-flops are not in active mode, or not going to be on state, not going to be in the on state simultaneously. They are not going to be in the on state simultaneously. That means they will not be in on state simultaneously. Okay, so there should be some condition. That is why it is called as asynchronous. Synchronous means all the flip-flops will be in on state at the same time. Okay, so that is the difference between asynchronous counter and synchronous counter. So all the flip-flops will not be in on state in asynchronous counter, and all the flip-flops will be in on state in synchronous counter. That is the name. That is why the name synchronous in that case, asynchronous in this case. Okay, now see the operation here. So clock pulse is directly connected to LSB bit. Okay, so here I'm taking flip-flop A, and here I'm taking it as flip-flop B, right? So flip-flop A is LSB bit. So if you want to write the counter values, you have to write like this, because this is LSB bit. Okay, so clock pulse is directly connected to flip-flop A, which is LSB bit, and you are making the JA and KA values as 1 for this clock pulse. I am talking only about QA. So initially both the outputs will be 0, initial states will be 0, right? Initially all the flip-flops are cleared. Okay, I am telling you how this asynchronous counter, 2-bit asynchronous counter works. So initially both flip-flops are cleared, and for flip-flop A, now we are giving J is equal to K is equal to 1. So JA is equal to KA is equal to 1. Then what will happen? Qn plus 1 is equal to Qn bar. Right? So when a negative clock pulse have been occurred like this, when negative clock pulse have been occurred, and you are giving J is equal to K is equal to 1, so the output toggles, that is output changes its state. So now 0 becomes 1. 0 becomes 1. And upon the application of another clock pulse, so second negative clock pulse, so this second negative clock pulse, what will happen? Again J is equal to K. We are not changing the inputs. J is equal to K is equal to 1 is constant throughout the operation. So J is equal to K is equal to 1 still continues, so the output will now becomes 0. So complement of 1 is 0, complement of 0 is 1, and next it again becomes 1, and next it again becomes 0. Okay, it again becomes 0, and so on, right? It continues. So this happens for the flip-flop A. Now if you observe flip-flop B, so it is now connected to through QA only. It is now connected through QA only. Yes or no? So it is now connected to QA. So when it is when will be this active state? So when QA is equal to 1 only. When QA is equal to 1, 1 given as input here, bubble operation will be there, so it will become 0. So then it will again becomes active because it is negative edge triggered flip-flop. So when QA is equal to 1, because this triggers this QA triggers this flip-flop. So QA output of this first flip-flop is connected to the clock input of the second flip-flop. So that's why, so second flip-flop will be in on state only when QA is equal to 1. Okay, so when QA is equal to 1, what will happen? So here QA value is 0, so its next state will be same as this. Right, now there is 1 here, right? So when 1 occurs, its next state is going to be changed, so it will become now 1. And again 0, when 0 is there, it continues its state, so it will be 1 state only. It will be continuing its state, right? So again there is 1 occurred, so it will again 0. So the next state of 1 1 is again 0 0, so counter will resets itself. Counter will resets itself. Okay, so counter counts from 0 0 0 1 1 0 and 1 1. So total number of states are 4 in number. So that is why 2-bit counter will counts from, as I have told you, it counts from 0 to 2 power n minus 1. Totally it will have 2 power n states. So here n value is 2 because we are using 2 flip-flops. So total number of states will be 2 power 2, which is equal to 4. So these are the 4 states which you have. And counter counts from 0 to 2 power n minus 1. 2 power 2 minus 1 is 3. So 0, 1, 2 and 3. 1 1, we know that its decimal value is 3. So it counts from 0 to 3. And after 3 it again resets to 0. So this is how it again resets to 0. So only condition which you have to remember is the flip-flop B. Flip-flop B will be in active state only when QA is equal to 1. Only when QA is equal to 1, like this. So initially both are 0. So since the counter A is 0, so its next state will be in the same state. So it will not change its state, because it is not driving enough. So here it is 1, so it will change its states. It will be 1 here. Now again the next state will be 0. So 0 means it will continues its state. It will not change. So it will continue. So previous state is 1, so it continues its state as 1 only. And since again 1 is occurred, so it will change its states to 0. That means the next state of 1 1 is 0 0. So counter resets again. So we are not performing anything, so counter resets on its own only. Okay, so this shows the timing diagram here. So if this is your clock pulse, upon the application of the first clock pulse, so until then, that point of time, so QA value is 0. So first negative clock pulse occurred, so it changes its value to 1. And again second negative clock pulse occurred, so it changes its value to 0. Again third clock pulse occurred, it changes its value to 1. Fourth clock pulse occurred, changes its value to 0. Like this. 0 1 0 1 0 0 1 0 1 0, same. Right. So here so as I have told you in this operation, so it will continues here 0. And since QA is not equal to 1, so if QA is 0, so at this clock pulse QA is 0, so it continues its states. So 0 0, so 0 0, like this. Here it is 0 and 0 1 1 0 0 0 1 1 0. Okay, so if you take this as T, time period this as T. Okay, so time period here, if you take it as T, from one clock pulse to other clock pulse, if you take the time period as T, then what is the time period of this signal? So time period will be from here to here, yes or no? From here to here. So what is this time period? This is 2 times of T, right? So from here to here it is T, and from here to here it is again T. So time period here is 2T. So time period of the waveform QA is 2T. And what is the time period of waveform, this waveform? So it starts from here and ends at here. So it will be 4T, 2 times of this. So it will be 4T. Okay, so when time period doubles, what will be the frequency here? So frequency here is f dash is equal to f by 2. If you take this frequency of the clock pulse is f, so frequency here will be f by 2. And what will be the frequency here? F dash is equal to f by 4. Okay, so there is a chance of asking the question. So if the input frequency is f in, here clock pulse input frequency is f in, what is the frequency at this stage? That is, what is the frequency of first flip flop is f dash is equal to f by 2. So what is the frequency after second stage is f double dash, if you take, it is equal to f by 4. Okay, so suppose if you have 20 kilohertz here, so the output frequency here will be 10 kilohertz. If you take here, it will be 5 kilohertz. Okay, so these are the important points which you have to remember regarding asynchronous circuit or asynchronous counter. Okay, so in the next video we'll discuss about 3-bit asynchronous counter. Okay, so I will give you a glimpse of that. So I have clearly explained you here, so I'll take the example there and explain you more concentration. I'll keep it on frequency terms. Okay, so this frequency division is very important. Okay.